Hello everyone, welcome back to another video of our multi-threading in Java series. In our last video, we solved the reader-writer problem. Now, even though we solved it, it was still incomplete with some limitations. Let's just recap the last class quickly within 1 minute and then I will lay down the agenda for today. Basically, our problem was to write a multi-threaded program to simulate the behavior of multiple readers and multiple writers reading or writing on a shared resource. Imagine we have a simple integer variable with value n equals to 2. Now at any point of time, multiple readers can read simultaneously from this shared resource because reading is indestructible operation because reading doesn't change the state of the shared variable. Therefore, we are allowed to have multiple readers reading at the same time. However, at the time of writing, when a single writer is writing on the shared variable, no other readers should read and no other writer except the one which is already writing should write on this shared resource. Correct? Because we do not want race condition to occur here. So in our first version, we tried to solve this using the synchronized wait and notify all keyword, right? But when we used synchronize, the correctness of the program was there, but readers were not able to read parallelly, right? So we saw these limitations. Multiple readers were not able to read parallelly at the same time. So to solve that, we tried to write our own custom ReadLock and WriteLock function. We built logic for our custom class for lock read, unlock read, lock write and unlock write methods. Correct? We built our own lock using synchronized only. So after building this solution, the readers were able to read parallelly. However, the writers were starving. So what we did? So to solve the reader starvation, we introduced another variable in favor of writers. How many writers are writing at a particular time? Then our writer starvation was solved, but our readers were again starving. So in our solution, either readers were starving or writers were starving. Correct? So to solve that, we quickly introduced ReentrantReadWriteLock class and just said that if we use this class, then reader starvation as well as writer starvation, both of these starvations will be solved. Correct? Now the point of the previous video was to understand the problem that we can have with our custom implementation, so that when we look into the Java's inbuilt provided class ReentrantReadWriteLock, we know exactly what it's doing under the hood and why every feature it has actually exists. So we are going to cover ReentrantReadWriteLock in this video completely, how it works, how it solves starvation for both readers and writers through a fair mode. We are also going to see several properties like reentrancy and lock downgrading that we get with ReentrantReadWriteLock. So by the end of this video, you will know exactly when to reach for this lock and when not to reach for this lock. Correct? So without wasting any time, let's dive into ReentrantReadWriteLock. Now, ReentrantReadWriteLock lives in java.util.concurrent.locks package. This was introduced in Java 5 and it contains two inner objects, ReadLock and WriteLock. Let's see what these two have. Let's understand these locks with an example. Suppose you have 5 threads, T1, T2, T3, T4 and T5, correct? And you have two locks, ReadLock and WriteLock, correct? So there are two scenarios here. First, let's see scenario 1. In scenario 1, initially, suppose thread T1 comes and T1 tries to acquire ReadLock. At that time, what will our reentrant ReadWriteLock class do? This is short form that I will be using, RRWL, for reentrant readWrite class. What will this class do? First, this class will check, is ReadLock acquired by any other thread? No. WriteLock acquired by any other thread? No. And therefore, T1 will be allowed to acquire ReadLock and perform its operation. Then T2 will come. T2 will go ahead and again try to acquire ReadLock. What will happen? RRWL class will go ahead and check whether any other thread is using WriteLock or not. And none of the thread is using. Whether any other thread is using ReadLock or not. Actually, T1 is using ReadLock, but we don't have a problem because ReadLock is actually a shared lock which can be accessed by multiple threads at once, which we will use for reading, correct? Because we want multiple threads to read. So actually, the RRWL class will allow T2 to go ahead, acquire the ReadLock and perform its operation. Now suppose T3 comes. T3 also tries to acquire ReadLock. Again, ReadLock is acquired by T1 and T2, but no problem. T3 will also be allowed to acquire ReadLock and perform its operations. Now suppose T4 comes. Now suppose T4 comes and it tries to acquire WriteLock and perform its operations. Now at the time when it tries to acquire WriteLock, what will RRWL class do? The ReentrantReadWriteLock class will go ahead and check whether there are other threads which are already active and have acquired the ReadLock. If there are other threads which have already acquired the ReadLock, then we will not allow any other thread to acquire WriteLock and perform its operations, correct? We will block thread 4 until and unless T1, T2 and T3 performs their operation, read operation and release the ReadLock. Until then, we will block T4, correct? Now if T5 comes and tries to acquire the WriteLock to perform its operation, it will not be allowed. However, if T5 wants to acquire the ReadLock, T5 will be allowed to acquire the ReadLock and perform its operations, correct? So ReadLock is shared lock, correct? And whenever a ReadLock is acquired by another thread, until and unless it is released, no other thread will be allowed to acquire the WriteLock, correct? So this is how it works. This is the first scenario. Now let's go ahead and check the second scenario. In scenario 2 as well, suppose we have 5 threads, a ReadLock and a WriteLock. Now what happens? Suppose T1 comes first and tries to acquire the WriteLock. At that time, what will RRWL class see? It will check none of the other threads are acquiring the ReadLock, correct? None of the other threads are acquiring the WriteLock as well. So both of this lock is completely open to be acquired. Therefore, T1 will be allowed to acquire the WriteLock and perform its operations. Now at the same time, after this, if T2 comes and tries to acquire the WriteLock, what will RRWL check? It will check whether any other thread is acquiring the ReadLock or not. It is not. Cool. Whether any other thread has already acquired the WriteLock or not. Actually, T1 has already acquired the WriteLock. Therefore, T2 will not be allowed to acquire the WriteLock and perform its operations. And T2 will be kept in wait state. Correct? Now suppose T3 comes and tries to acquire the ReadLock. What will RRWL class check? It will check whether any other class has acquired the ReadLock or not. It has not. Okay, so it can be acquired. But the second condition is whether any another thread has acquired the WriteLock and is currently performing an operation or not. It will check, yes, T1 is a thread which has acquired the WriteLock and is performing some write operations. Therefore, we cannot allow T3 to acquire ReadLock and perform the read operations, correct? Therefore, T3 will also not be allowed to acquire ReadLock and perform its operations, right? So this is the second scenario. So when we combine both of this scenario, what we get? Actually, we have two types of lock, ReadLock and WriteLock. The ReadLock is shared, where multiple threads can hold this simultaneously. We saw in scenario 1. But it is blocked only when WriteLock is held. In our second scenario, when WriteLock was already held, then no one was allowed to acquire the ReadLock, and that is what is written here. For our WriteLock, our write lock is an exclusive lock, which means only one thread can hold it at a time. Correct? And the second condition is blocked when read lock or write lock is held. So we can see here in our first scenario, when the read lock was held, no other thread was allowed to acquire the write lock. And in our second scenario, when our write lock was also held, no other thread was allowed to acquire the write lock again as well. Correct? So this is blocked when read lock or write lock is held. So these are exactly the two types of locks that we have built in our last class manually. However, Java directly provides this, and all the internal implementations of incrementing the writer, number of writers present, and all those coordination things are handled by ReentrantReadWriteLock class. Correct? So the usage of this is very simple. What we have to do? This is the syntax of how we can use ReentrantReadWriteLock. So what you have to do essentially? You just have to create an instance of ReentrantReadWriteLock. Then you will extract two lock from it using readlock and writelock method, which will be readlocks and writelocks. Correct? Reader will use simply write readlock.lock whenever it wants to read, and after reading it will do readlock.unlock. Correct? Writer will do writelock.lock and writelock.unlock after it has completed writing. Very simple. Correct? So you will use these locks independently in your reader and writer code paths. However, in the background, they will be completely in sync with the help of ReentrantReadWriteLock. Correct? One rule you must never break is you always have to unlock the lock which you have acquired in the finally block. Why? Because if any exception is thrown inside your critical section, you don't release the lock, every other thread will be waiting on this lock forever. And that is a deadlock which will be very hard to debug on production systems. Therefore, always remember to do readlock.unlock inside the finally block. Correct? So keeping these things in mind, let's go ahead and rewrite our shared resource class that we formed in our last video. If you haven't watched the last video, I highly recommend you to go and watch that. Only then you will get the context of this video. Right? You'll see how simple we'll tweak our shared resource class and it will get converted into RRWL class implementation. Correct? So let's go on our IDE and code that. Right? So what we'll do, let's create another package named. Correct? In this, we'll have a main class and we'll have a shared resource class. Our shared resource class, most of the things will be exactly same. So we'll just copy this and in our new shared resource class, we'll paste this. Right? What else? Instead of using custom read-write-lock, we will use ReentrantReadWriteLock. So here we will do ReentrantReadWriteLock RWLock equals to new ReentrantReadWriteLock. Correct? Then what we have to do? We have to extract the read lock and write lock from this. Correct? So we'll write this read lock and write lock is extracted. While reading, what we'll do? We'll acquire the read lock. Correct? And in the R finally class, we'll do readlock.unlock. Correct? In our write class, write method, what we'll do? We'll do writelock.lock. WriteLock.lock and here WriteLock.unlock. Correct? This is all the change that we need to do here. Correct? So if I go in my main class, I'll go here and I'll copy the main class as it is. Correct? Main class, let's copy it. Now shared resource, we have to use the one which we have just created. Let's remove this from here. Executor service shared resource dot write, correct, and shared resource dot read. Right? Let's comment this infinite loop for now. And so we have only 4 tasks for reading and 1 task for writing, correct? I think this is all right. Now let's go ahead and run this and see whether we get the expected output or not. Correct? So once we run this, we see multiple threads are there. Multiple threads are reading simultaneously, and only when they are finished, we have started writing and we have finished writing as well. Now, this was working in our custom read-write lock as well. Correct? Now let's test this with multiple threads. Multiple tasks of reading and writing when this goes into infinite loop. Let's see whether the starvation problem still exists or not. Okay, now what we see? We gave a complete lecture about reentrant read-write-lock solving starvation, but we see here initially all the reading has happened in parallel, which is perfectly fine. Then writing has happened, and post that writing again and again, only writing is happening. But to our surprise, after some time, again reader gets chance and then writing, correct? So reader got chance here, writer got chance here, but there is a possibility that reader might never get chance, correct? This brings us to second property of reentrant read-write lock, which is the fairness thing. So inside our shared class, if we just go ahead and write true here, this will ensure fairness. So after writing, our reader threads which were waiting on the lock will get chance to read again. Correct? Now if I go ahead and run this, I'll see a different output. That output is all the reading has happened in parallel. Then we have wrote also. Again all reading has happened in parallel. Then writing, reading, writing, right? So alternatively, all the threads which were waiting are getting fair chance to read and write, correct? So the first property was we had 2 types of locks, read lock and write lock. We just wrote it and all the internal implementations were handled in the background. Second property is it also ensures fair mode. So if we go ahead and write true here, then we can ensure fairness and reader and writer will get equal chance to read and write. But how this fairness, this second property works in the background? What is the underlying data structure that helps reentrant read-write lock to maintain fairness? Let's go on our blackboard and see this second property of reentrant read-write lock. So the first property is it provides read lock, a shared lock, and write lock, an exclusive lock. Correct? Second is it provides fairness. So how does RRWL achieves fairness, or we can say how does RRWL handle starvation? So reentrant read-write lock has 2 modes. One is a non-fair mode, which is the default mode, and another is a fair mode. And fair mode is achieved by passing true in the constructor parameter. So when there is non-fair mode, what are the problems? There is no ordering guarantee. When the lock is released, threads compete freely without any restriction. Therefore, there is a risk of starvation. And this non-fair mode is used when you require high throughput. Why? Once we explain this, you will get to know why. In the fair mode, reentrant read-write lock strictly uses a FIFO queue. So thread are granted access in the order of their arrival, and therefore nobody starves. Both readers and writers both are protected. And since it follows this slow approach, therefore it gives slightly lower throughput. Let's see an example. Suppose your arrival order for acquiring the lock is reader 1, reader 2, then writer 1, reader 3 and reader 4. So in non-fair mode, what can happen? Suppose reader 1 and reader 2 are running together. Now the next chance should be for writer 1, but since this is a non-fair mode and all the threads are competing freely, therefore reader 3 and reader 4 might jump ahead of writer 1 and acquire the lock, which will mean that writer 1 could starve. Therefore, the fair mode was introduced. In fair mode, this is the order in which threads have arrived. So, reader 1 and reader 2 will get chance first. Since both are readers, both will run together, Both are at the front, therefore both the readers will get that chance. Now the second step is, when reader 1 and reader 2 has finished reading, the next in queue is writer 1. Writer 1 acquires the write lock and runs exclusively. Why? Because it is next in queue and we have toggled on the fair mode. Therefore, writer will run. After the writer runs, reader 3 and reader 4 can go ahead, acquire the read lock and can run in parallel together. Therefore, writer is already done and nobody starves, neither the reader nor the writers. Correct? So this is the second property. The third property of reentrant read write lock is it provides monitoring methods. Methods like is fair, whether fair mode is on or not. Get queue length. How many threads are currently waiting in the queue? Get read lock count. How many threads hold the read lock currently? And similarly, we also have get write lock count. Then the next method is write locked. Is write lock is currently held or not? So these are some monitoring methods that RRWL class provides. Now the fourth property is reentrant read write lock also provides reentrancy. So reentrancy is inherently built inside reentrant lock, and since RRWL uses reentrant lock, therefore it provides reentrancy. Now what does reentrancy means? It means it allows the same thread that already holds the lock to acquire it again without blocking itself. Consider this example. Suppose we have a thread which has called this method outer write and it has executed WriteLock.lock. So it has acquired the lock once, correct? Then it has printed get writer hold count. The value is 1. Then it has called another method which is inner write. This inner write method again goes ahead and write WriteLock.lock. So it is again trying to acquire the same lock which has already been acquired by the same thread. And this is allowed here because it is same thread itself, right? Therefore, it is allowed, no deadlock is there and the hold count is increased from 1 to 2. Therefore, get write hold count will print 2. Now the main part to notice here is the lock tracks a hold count, how many times the current thread has acquired it, and it fully releases only when unlock has been called as many times as the lock. So once unlock will be called here and another unlock will be called here. So 2 times lock is called, 2 times unlock is called, and then the lock will be considered as released for that particular thread. Correct? The fifth and the very important property is lock downgrading is supported. Now what is lock downgrading? So there are two concepts here. One is downgrading and upgrading. So in our above example, what we have done? We have written, we have acquired write lock and again we are acquiring the write lock. What we can do instead is, once we have acquired the write lock, we are also allowed to acquire the read lock with the same thread, right? So what do I mean by this? Suppose this is method 1. You have called write lock, correct? Then you are calling method 2. And inside method 2, you are calling ReadLock dot lock. Here also dot lock, correct? So if a thread has acquired the write lock and is then trying to acquire the read lock, that is supported inside RRWL class. But the opposite is not true. So this is called as lock downgrading. We are downgrading from write to read. But if a thread has already acquired a read lock and it is trying to acquire the write lock inside, then that is not allowed, correct? How it works? Let's see. When you do ReadLock.lock, there is an internal check which checks whether a write lock is held or not. So after write lock, when we try to acquire the read lock, what will happen? Internal check is whether a write lock is held. Yes. Is it held by the current thread? Yes. If it is held by some other thread, then it will not be allowed. But if it is held by the current thread, then allow it. And this is downgrade. However, in second case, what will happen? After we have acquired the read lock, if you try to acquire the write lock, what will happen? It will check, is the write lock held? If it is not held, then fine. But if it is held, can write lock be acquired? No, because the number of readers are greater than 0, including the thread which is acquiring the read lock. Therefore, it will wait for the readers to clear. It will wait for itself to release the read lock. But since you are already waiting on the write lock, there is a deadlock. Correct? So read lock is waiting for write lock and write lock is waiting for read lock to be released. And therefore, this is not supported, but lock downgrading is supported. Very important property. So consider a scenario where you write some data and immediately need to read it back. So this is the scenario where you would actually require lock downgrading. So this is the sequence in which you should perform lock downgrading. So step 1 is you have to acquire the lock, right? Then step 2, whatever value you want to write, you will write it. Then the step 3 should be acquiring the read lock, correct? This is lock downgrading. While still holding the write lock, you want to call the read lock because you want to immediately read the data which you have just written. Now you could release the write lock and then perform ReadLock.lock as well. But the problem here is if you first write this unlock and then you write ReadLock.lock, then in this tiny gap, another reader could modify the data and your read might not see what you just wrote. Therefore, lock downgrading eliminates that gap. The sequence is very critical, right? So acquire read lock before releasing the write lock, and this guarantees that no other writer can sneak in between your write and read, correct? We also discussed never do the reverse, correct? Never read and then try to acquire the write lock. Why? Because acquiring write lock while holding the read lock will cause deadlock. Now let's see the limitations of reentrant read-write-lock. Now internally, reentrant read-write-lock maintains a shared state. So the first limitation is read lock still has overhead. Now how does read lock has overhead? So internally, the reentrant read-write-lock maintains a shared state variable, right? This variable tracks down how many readers are currently active, correct? Now, every time a reader enters or exits, it must update this counter. And because multiple threads are doing this simultaneously, the update to this counter must be atomic, right? Now, to maintain atomicity, we use something called as compare and swap operation. Now, you can read this CAS operation by yourself. It's very simple. But the main point to understand here is it has an overhead associated with it because we want to maintain atomicity on this state variable. So when there are multiple readers, then this overhead can be very significant, correct? And therefore, this is the first limitation. Now the second limitation is there is no optimistic reading. Basically, reentrant read-write-lock has no way to say that let me try to read without locking, right? Let me try to read without locking and only lock if something went wrong, correct? And even if the probability of write happening at the exact moment is almost zero, still you will end up acquiring the lock and then releasing the lock, right? So in a system where writes happen once every few seconds, then is it really necessary to acquire a lock on every single read? If there is no write happening, what is the point of acquiring the lock? Correct? So the answer of this question should be no, but RRWL has no mechanism for this, correct? Therefore, we say there is no optimistic reading, right? So the case where it should not have acquired the lock because there are no writes currently happening, the probability is very low, still it is forced to acquire the lock, right? Now the third thing is fair mode. Fair mode reduces throughput. Why? Because it forces strict FIFO ordering using a queue, correct? And since strict FIFO ordering is forced, the readers that could have been batched together are forced to wait. And since the readers are forced to wait, therefore the throughput decreases, correct? Now all these limitations points to a natural question. What if in a read-heavy system, we could read without acquiring any lock at all and only fall back to the real lock when absolutely necessary, correct? So my friends, this is where a new concept is being introduced in Java 8, which is called stampede lock. And this stampede lock solves the limitation of acquiring the lock again and again, even in a read-heavy system. And this stampede lock is the agenda for our next video. So I hope you are clear with this video. So we have studied reentrant read-write locks in detail. We have studied the properties, how we can solve reader-writer problem using that. We have studied the limitation, right? So we have studied everything, and this is more than what you will be asked in the interview, but still it is very good if you already know the core concept that is running behind this read-write lock, correct? So I hope you like this video. If you like this video, please share this with your friends and please hit the like and subscribe button. I'll see you in the next video. Until the next video, stay safe, stay healthy. Bye-bye.